matrix multiplication. So we've discussed already many matrices, different examples, and we already know that matrices are linear maps in the sense that they take a vector, they can scale it and move it around and so on. And now we have two matrices that are being multiplied by each other. How is this defined? Or how should this be defined? Well, to make sure we have the clear intuitive understanding of this, it is simply the composition of two maps. So we know matrices are linear maps. You multiply a matrix by a matrix, then you're composing these two maps into a third map. Just like you would compose two functions, for example. So this is good. I'll start by doing the algorithm, show you how it's done, and then we can have some discussion about what it actually means and why it is defined the way it is defined, which I think is something that is not standardly discussed. But I'll leave it until the end so that if you're not interested, totally fine. Matrix is just a matrix. And so here's how we proceed. Usually it is as follows. So the matrix, if you want to do it, just for the exam, just want to know how it's done. It's as follows. So you take the row with the column, and the place at which they intersect is this part is the place where you place the result. So it's kind of like an array where you can store dot products of vector, row and column vector. I do the same thing. I move this here, then they meet in the middle, and then write for the middle term 1, 2, 9, and then -1, 1, and 1. I do this 7 more times. Seven more times in the sense that I will continue like this. These are dot products, if you're curious. Let me write all of them down, and then we can take a good look at it. I'm not sure if you see this, but you really do take the column and you copy it 3 times. And you do the same thing here, here, and there. And for the first matrix, you just do it for the rows. That's also not a bad way to think about it. So this is how you should proceed. For each coordinate in this matrix, you will get a 3 times 3 matrix. And this 3 times 3 matrix should look like this. So for example, if we just do one example of a dot product as an example. This dot product is as follows. So you take the first component with the first component, second one with the second one, third one with the third one. You get 1 times 1 plus 2 times 1 plus 9 times -1, which is, I think it is -6. You can do this for all the indices in this matrix, and you should get the following result. Because it would be silly to watch me compute all of this. I think that would be very silly. So I'll just give you the answer here. -6, 10, 8, 2, 6, 4, 5, 9, 7. Yes, so this should be the answer that you would obtain. You should try to do it for all of the remaining entries and see if this is indeed what you get. If it's not, maybe there's a mistake, you can try again. But the idea is very simple and it's very straightforward, I would say. It is simply that you take the rows with the column, and the place where the row and the column intersect is where you place this dot product. And it's always a dot product. So you just need to compute lots of dot products. But if they're just dot products, then it is nice. I think everyone loves dot products. I think they are much more friendly than big matrices. But matrices are just has data of different dot products. And if you think about it in this way, then algorithmically you should be able to solve it pretty quickly. Now, if you're still here, I would like to say a few words about why this is defined the way that it's defined. And so I think it feels a little bit unintuitive to consider this setup of row vectors and column vectors. It feels very arbitrary and unmotivated. And I would like to motivate it now by what I'm going to proceed with. And so first I want to brush up on how originally we defined multiplication of a matrix and a vector. Because fundamentally the way we've defined matrices as linear maps, we imagine the action of a matrix on a vector as the dot product of a vector with a vector of vectors. For example, I would like to consider the product of applying this matrix transformation to an arbitrary vector, which I'll call xyz. We know that this will be as follows. This is how it's defined. You take the first component with the first component, second one with the second one, third one with the third. This is how it's defined. If you know how it's done, then this is good. But if you've never asked yourself why this is the case, then let me tell you. I'll even color these in green. I want you to focus on how they're related to the values in the matrix. So this is the first row. This is the second row, and this is the third one. Now it turns out that I can actually take this and write it in a more compact form. Specifically, I see that here I'm multiplying xyz by 1, 1, minus 1, and 1, because just by comparing the coefficients, I can tell that this is what's happening. So this is the first component in our vector, in our resulting new vector. Second component is xyz, but with the second column. No, is it the second column? It's not. It's the second row. And I would like to signify this by writing this vector horizontally. And you will see now where the row vector comes from. So what I'm doing right now is I'm writing this as a dot product, but I'm deliberately writing this vector horizontally. If you read this off, 1 minus 1 and 1, this is the row vector in this matrix. I do this 2 more times, and this is precisely what I can obtain. I obtain the values for the rows in here. You can check this yourself, of course, if you're not sure about what I'm doing right now. Just need a little bit more space, and then it's good. So this is effectively what's happening when we multiply a matrix by a vector. Well, the opposite, we're multiplying the vector by a matrix. We're just taking dot products. I'll even take this one step further. I want you to notice that I can actually write this as x, y, z, and then I write a matrix of matrices, which I've talked about now for some time, hinted at, but not talked about perhaps. And this is a vector of vectors that looks like this. So I take the column vectors and I turn them into entries into my vector. And this vector is a vector of vectors. And I deliberately write the entries horizontally to ensure that you can see that if I actually remove these things, I get my matrix that's right here. So it's like I take the columns of the matrix, I turn them into entries, and then I take the dot product. What happens when I take the dot product? Well, here's what. So the dot product goes as follows. It's the first entry with the first entry. This is the first, and this is the first. So what I'm going to do now is going to justify why this row appears, even though we're usually multiplying, columns and thinking about columns. So here's why. Take the second component with the second component. Now I hope this is not too weird. I know that the second component is a whole vector, but just bear with me. And the third component with a whole vector like this one. And then we obtain this or that when we distribute the constants. You could think of x, y, and z as constants, which we scale the elements of each vector by. So if I do this in one big vector, so perhaps this is a vector. I shouldn't write it as with these thingies, because these thingies usually signify matrices, and this is a vector. So this looks weird, but it's a vector. And here's what's going to happen. I multiply x by 1, and then I add y times minus 1. So x times 1, and then I add y times minus 1, and then z times 1. Does this look familiar? Yes, I hope it does, because this is precisely that. So they are equivalent. They are equivalent. This is kind of, I don't want to say a proof, but it is a proof if you think about it. And you can, of course, check that if you distribute and collect the terms in each respective entry, then you will get the exact same setup that's here. Because, you don't need to distribute only for the first coordinate. We can distribute for all of them and then add, and then we would get the same result. So why is this useful? The only reason I'm mentioning this is because I want to give you a certain perspective as to why we have a row that's being multiplied by a column vector. Because usually we multiply column vectors by column vectors in a dot product. And yes, I mean, this is indeed the case, but we just consider the row vectors as column vectors, and we apply the dot multiplication, the dot product. So this is a good perspective on it. Now, what happens if I take this matrix multiplication and I do the following. So I take this and I apply to it another matrix. Well, not another, the other matrix. We should be able to get the same result that we obtained earlier here, right? Let me actually copy it for the sake of reference. I think it was minus 6, 10, and 8. 2, 6, and 4. And then 5, 9, and 7. Because I think what's about to happen now is almost magical. I think you'll really like this. So let's go on and multiply both sides by this matrix. So remember, the resultant from this matrix vector multiplication is a vector. This is a vector. This is exactly that vector. It looks weird, but this is a vector. And I just write it in this, you could say, compact form. I don't think it is compact, but you could say it is compact. I take this vector on the right and I apply to it my matrix, which is on the left here. What do I get? And that is a good question to ask. I don't want to proceed with the standard. Well, you can proceed with any way you want. I personally do not wish to proceed with the standard matrix multiplication. I want to proceed with the way that we've intuitively understood together. And this is precisely as follows. So what we did originally in this smaller area is we took the rows of the matrix, we composed them with the intended vector in a dot product. This is precisely what we did. And now I will do the exact same thing. So, not to get confused, we took the original vector, okay? So this is the original vector, all of it. We took all of the original vector, which is this one. It was this one. It was this purple one. Perhaps some color coding would be very helpful here. This is our new vector. This is our matrix. So I take the vector as it is, and okay, since I have space, maybe I can just put it 3 times. And after writing this vector down 3 times, what we did is we multiplied each respective entry by the respective row in the new matrix that we're trying to apply. So to recap, we had linear transformation and the vector. We put the vector here and we applied the transformation by multiplying respectively by each row. So I will do just that. This is my vector. It's a weird vector, a very long vector. And now I will multiply it by the respective row in my new matrix. So this is 1, 2, 9. This is 3, 4, 5. And this is, well, it's the final row in my new matrix. Is 6, 7, and 8. Now, what should this give me? is a good question to ask. Let me tell you what it should give you. So the answer in this case is to precisely treat the entries of the vector, the very complicated vector that we have here, as constants. And I'll make this clear in just one moment. Just trying to get us a little bit more space. So we do this, and this is the first entry in my vector. It looks very weird, but this is the first entry in my vector. I scale it by the first entry in the other vector. Remember, this is a dot product. I do the same thing with the second vector, scale it by the second entry, and I do this one more time with the third entry. So I get the following. Just try to ignore the other parts for now. Let's just focus on this one. So for this one, we agreed that we're going to scale the first one by 1, we're going to scale the second one by 2, and we're going to scale the third one by 9. We scale this by 1, we scale this by 2, and we scale this by 9. And remember, with the dot product, we always add, to get the final result. Now all of them have x, y, and z, so probably we shouldn't worry too much about it. And now here's where the magic happens. So I scale this by 1, just remains as it is. I scale these by 2, so I get this by 2, and I scale this by 9. And I add all of them. Then this should give me x, y, z as it is, right? Dot product with, so I can add these first, because in the end this is more or less a common factor that's taken with x, y, z. I can add the entries, and when I do this I get 1, 2, and minus 9 is minus 6. 2, 9, and minus 1 is 10. And finally 1 minus 2 and 9 is 8. And guess what? Minus 6, 10, and 8 is what's right here. And I would like you to check that if we proceed similarly for the other two matrices and we apply the proper scaling, then we would obtain 2, 6, 4, and 5, 9, 7 as we did here with the other two matrices. And then I can say with great confidence that if I, for example, would like to find the first 3 rows in my matrix, then I would be looking at following. We know that this has already given us minus 6, 10, and 8. And we know that we should proceed by applying this vector to not to each one of these scalars, but in this case we should consider this vector format of the matrix. And then we apply a dot product. And this is where the multiplication of the row by the column comes from. This is why we multiply 1, 2, 9 by 1, 1 minus 1 to get the first coordinate. And then we do it again to get the second coordinate, and then we do it one more time to get the third coordinate. Watch this. We know this is minus 6, 10, and 8 on one side, and on the other side, this is precisely a vector. Because remember, this is a vector being multiplied by a vector of vectors. So I get this as my first entry. This is my second entry. And this is my third entry. And as we've just seen, perhaps if you're not sure, so this dot product of vectors will give you minus 6. This dot product of vectors will give you 10. And this dot product of vectors will give you 8. So this is a really, really solid proof that this is precisely how we should proceed. Of course, this is, applicable to the other rows and the other columns. And if we do this if we even want to write the whole matrix, just like we did up top, we would write it as follows. This is what we did in the very beginning. So we're storing dot product of terms 1, 2, 9, 3, 4, 5, 6, 7, 8. So I hope this was some insight into why this works and how this works, because I feel like most of the talk about matrices and matrices with matrices and matrix treatment in general is very raw and very empty, and I don't like that. So I wanted to give some ideas, I want to get some ideas across. I hope I was successful in doing that. I wouldn't be surprised if this was not immediately clear from the first glance. I think this is completely understandable. And I don't even think it is necessary to understand all of it. But I felt that you would have a much, much, much stronger foundation if you proceed as well. So to conclude, I include the exact same snippet that we had at the very beginning, and this is precisely it.